The venous return cardiac output curves are probably one of the most confusing concepts for students studying cardiovascular physiology. It is also one of the most important. In order to understand the venous return and cardiac output curves, you really need to have some knowledge of the conflicts between philosophies at the time that these were presented by Dr. Arthur Guyton in 1955. At that time, there was a lot of work being done on the function of the heart. There were also others who were focusing on the regulation of blood flow in various isolated organ beds, such as the gracilis muscle. The question at the time was what actually controls cardiac output, the heart or the peripheral tissues. Those in favor of the heart said that it controlled its own cardiac output, and thus cardiac output to the tissue was controlled by the heart. The other group said that it made no sense for the heart to tell the tissues what they needed, so the heart was the servant of the peripheral tissues. The idea of coupling the two systems was somewhat new, and it was in this environment that Dr. Guyton did his experiments, looking at the relationship between the heart and the tissues. In order to understand what was being presented, you had to look at the tissues rather simplistically as a pump in series with the high pressure, low volume or low compliance system, the resistance vasculature, and the high volume, low pressure system, or the venous system. With this in mind, Dr. Guyton's group took dogs and denervated the heart so that they could control cardiac output by controlling the heart. They then recorded blood pressure and central venous pressure as they decreased cardiac output. This kind of experiment is shown here, where they are decreasing the pump or the heart and seeing that arterial pressure decreases and that venous pressure increases. As the pump is slowed down, the blood pressure decreases and blood is backed up into the venous system. To look at it another way, as you increase the cardiac output, the venous pressure decreases and the arterial pressure increases. This puts a rather different spin on it. However, when the pump is at zero, the system is at equilibrium. Since there is no resistance to flow, the pressure through the system is the same and is determined by how full the system is. They called this pressure the mean systemic filling pressure. As my mentor, Dr. Harold Green, was not a big fan of Dr. Guyton, he called this the dead dog pressure, since that's the pressure that was in the dog when they died, and that's how they determined it. Dr. Guyton then did what any good physiologist would do, and that was that he plotted these data. This shows that as you increase the cardiac output, here going from 0 to 1, the venous pressure goes down. As you increase the cardiac output from 1 to 5, again, the venous pressure goes down. This figure has always been the real bane of students because it violates a very basic principle of graphing data. It puts the dependent variable, venous pressure, on the x-axis and the independent variable, cardiac output, on the y. Thus, as cardiac output increases, venous pressure decreases. The rationale for doing this was so that he could overlay the Frank-Starling curves on top of this and show how the two interacted. If you look at the figure and say that as venous pressure goes down, cardiac output goes up, you'll be confused and frustrated. So just remember that the x and y, or the dependent and independent variables, have been switched. An important point to understand is that the relationship between cardiac output and venous return is a straight line. As you increase the pump, it doesn't change what is happening. As you increase the pump, it doesn't change what is happening in the resistance vessels. As the pump increases, pulling more volume out of the veins, the pressures in the veins will go down below atmospheric pressure. And so at zero pressure, the curve flattens out, and it doesn't matter how much you suck on the veins, you can't get more volume out of them. And thus there is a flat portion of the venous return curve at the point that atmospheric pressure collapses the veins. The next thing that they did was to look at the relationship between venous return and the volume in the system, or the mean systemic filling pressure. Here you can see that at the normal situation, mean systemic filling pressure is 7. Since the mean systemic filling pressure is determined by the blood volume, it shifts along the x-axis as volume is changed. However, this shift along the x-axis does not change the resistance or the slope of the curve, since that is all pre-capillary. When total peripheral resistance, TPR, is changed without changing volume, the venous return will either increase or decrease. So vasodilation is going to shift this curve upward. Venoconstriction is going to shift the curve down. This is always a little confusing to the students, because you expect that as resistance goes up, the curve shifts upward. Just remember that they're just opposite of each other. Thus, venous return can be either increased or decreased by changing either the mean systemic filling pressure or the resistance in the system. And they can change simultaneously, and more than likely do as they work together. The entire purpose of all this was to provide a model that tied the systemic system to the heart. The venous return curves only represent the systemic system. The venous return curves show how much blood the heart will have to work with. In other words, venous return defines preload. Now we can link the systemic system to the heart. We can look at the relationship between the heart and the systemic circulation. In 1904, Otto Frank published his work on the relationship between venous pressure and cardiac output. He did his work in the isolated frog heart. In 1918, Ernst Starling, along with William Bayliss, published their work on the law of the heart. Their work was similar to that of Frank, that was done in the dog heart. The relationship between the preload and the strength of contraction, when plotted graphically, gives us the Frank-Starling curve. It is important to note that as right atrial pressure increases, cardiac output increases. This then places atrial pressure, which is the same as venous pressure, on the x-axis on both graphs, and allows us then to overlay the two. Right atrial pressure was used because it is easier to measure and changes proportionally to left atrial pressure, which is the left ventricular preload. The Frank-Starling law of the heart states that the heart will pump all that it gets. This also defines the failing heart, since if it cannot pump all it receives, then it's in failure. Now we can talk about these two systems and how they interact. The venous return curve addresses how much volume is available for the heart to pump. The Frank-Starling curve defines what the heart can do at a given preload. Thus, the venous return curve defines what's available to pump, and the Frank starting curve defines the ability of the heart to pump at any given preload or venous pressure. This intersection of the two curves defines the actual cardiac output, because this is the point where venous return and cardiac output are the same. Therefore, on this figure, right atrial pressure is 2 and defines the cardiac output of 5. The question now originally asked can be answered. What is controlling cardiac output? It doesn't matter how capable the heart is at pumping if there is nothing to pump. Since the tissues control their own blood flow by the process known as autoregulation, tissues regulate venous return and thus cardiac output. As we look at the venous return curves, we saw that venous return can be changed by changing either mean systemic filling pressure or total peripheral resistance. The ability of the heart to change its pumping ability is defined as contractility, showing the efficiency of the heart. In the 1950s and 60s, Sarnoff and Gilmore showed that there are actually a family of curves. These can be overlaid on the cardiac output venous return curve, showing that the heart can increase its efficiency or contractility, thus changing cardiac output. Increasing contractility pours more blood out of the veins and decreases venous pressure. However, the cardiac output is still determined by the intersection of these two curves. One more point to be made about the Frank starting curves. If you overstretch the muscle, the actin and the myosin overlap becomes less efficient. This is known as the failing limb of the Frank starting curve and has been well documented. The cause of the failing limb was recognized early as a result of overstretching of the sarcomeres. However, when Dr. Guyton drew his Frank starting curves, he didn't show a failing limb. His rationale for showing no failing limb on the Frank starting curve is that there is no failing limb in the acute heart because overstretching is prevented by the pericardium and the connective tissues of the heart. Undoubtedly, as the heart continues to overstretch in the chronic situation, then you do get a failing limb, and this is shown in his presentation of heart failure. I hope that this has been valuable to you and has assisted you in understanding the relationship between venous return and cardiac output.